Welcome back to the deep dive. Today we are putting on our thinking caps to really get into the architecture of modern thought itself, computer science.
That's a great way to frame it.
Our mission here is to understand that fundamental process, the precise steps you need to take an abstract problem and turn it into something real, a functional program.
And that transformation is really the core skill. Computer science, it's so much more than just tapping away at a keyboard. It's a disciplined synthesis.
A synthesis of what, exactly?
Well, we borrow from mathematics to create these formal logical languages.
Hmm.
We use engineering principles to design systems to evaluate trade-offs. And, we even use the scientific method
How so?
by observing, forming a hypothesis, and then testing predictions to see if our solution actually works. It's this incredible mix.
It's a truly multidisciplinary skill, and our sources make it so clear the single most important ability is just problem solving.
Yeah.
It all comes back to that. We're here to give you the blueprint for how to think like a computer scientist. Okay, so let's unpack this. There's a foundational trio that makes everything possible. Problems, algorithms, and programs.
Right.
It all has to start with the problem, right? A computational problem is really just a question that needs a very precise answer.
Exactly. And the complexity of these problems can be, well, all over the map.
Yeah,
You could have a super simple one, like what's the sum of 9 and 999?
easy enough.
Or you could have something incredibly complicated, like finding the absolute shortest path from San Francisco to New York City.
And not just on a map, but with like real-time traffic data.
Right, a massive, constantly shifting network. But regardless of the complexity, the first step is always the same.
Analysis.
Analysis. You have to understand the problem fully, its requirements, its constraints, all of your assumptions. You do that before you even think about writing code.
And once you've defined that problem, then you move to the algorithm.
Yes. The algorithm is the step-by-step process. It's the recipe to solve that specific problem. It has to be completely unambiguous.
The source material had this great example with a Martian.
Oh yeah, the Martian friend trying to buy groceries. It's perfect.
So your first attempt at an algorithm is, make list, drive to store, park, find items, check out.
And on the surface, that sounds fine. But if you gave that to a computer or our Martian friend who knows nothing, it would just fail instantly.
It has no context. What does drive to store even mean?
Does the car have gas? Does the Martian have a license? Did you even start the car first?
Right.
Each of those high-level steps is just a placeholder.
So the algorithm needs this. Aggressive refinement.
Aggressive is the right word.
Hmm.
You drill down and down until there's zero ambiguity left.
And once that recipe is totally foolproof, that's when it becomes a program.
That's it. The finalized algorithm gets converted into a sequence of computer instructions or statements, and that's your program.
Okay, here's where it gets really interesting for me. Every single program, no matter the language, is built on just a handful of fundamental concepts, like 6 of them.
Right. And you can almost group them into 3 bigger ideas.
Go on.
First, you need a way to handle information. So that's your data and your variables.
Variables are just names for boxes to store the data in.
Pretty much. They're human-friendly names for memory locations. So that's concept number 1, storage.
Okay, what's the second big idea?
Interaction. How does the program talk to the outside world? That splits into 2 things. Input, which is getting data.
From a keyboard, a file, whatever.
Output, displaying the answer on a screen, saving it. You need to get things in and get things out.
So we have storage and we have interaction. What's the third?
This is the big one. Logic and action. This is where the work happens. You need basic math. You need conditional execution.
The whole if this, then that idea.
Exactly. Testing conditions. And finally, you need repetition. Loops. The ability to do something over and over again.
And with just those things, storage, I/O, and logic, you can build almost anything.
You really can. Those are the building blocks of all computation.
Now, those instructions are written in what we call a programming language.
Which is just a formal language for creating that program. We usually split them into 2 main camps.
High level and low level.
Yep. High-level languages are the ones programmers prefer. Think Python, C++, I, Java. They're designed to be friendly.
They hide a lot of the messy details.
They do. Which makes them simpler to write, easier to read, and most importantly, they're portable.
Portable meaning you can run the same code on different kinds of computers with just a few changes.
Or no changes at all, ideally. The downside is that they need to be translated, which can take time and maybe run a bit slower.
And the other camp, low-level languages.
That's stuff like machine code or assembly. It's what the computer hardware can actually execute directly.
So they're incredibly fast.
Very fast. But they're a pain to write. You need to know all the low-level details of the computer, and they are absolutely not portable. You have to rewrite the whole thing for each different machine architecture.
Okay, so since we mostly use high-level languages, we need to translate them. And there are two ways to do that: interpreting and compiling.
That's right. An interpreter is a program that reads your code one line at a time.
So it reads a line, does the command, reads the next line, does that command.
Exactly. It's an alternating process. Python and JavaScript work like this.
And compiling.
A compiler is different. It reads your entire program all at once. It translates the whole thing into an intermediate format like bytecode.
And it checks for grammar mistakes at the same time.
Right. It checks your syntax. If everything is perfect, it creates this new file, which is then loaded into memory to be executed. C++ and Java are compiled languages.
Let's use C++ as our main example then to make this practical.
Good idea. It's a high-level compiled language, super popular for things where performance and efficiency really, really matter.
Like system programming, big, complex software.
Exactly.
But the language is just the tool, right? The core lesson here is the thinking process. I was really struck by that statistic in the research.
20% one?
Yeah, programmers spend only about 20% of their time actually writing code.
It's true. And that's where beginners make their biggest mistake.
They think it's all about the typing.
They jump straight to implementation. That other 80% of the time, that's the essential systematic process. It's what turns this from a hobby into an engineering discipline.
Okay, let's walk through that process, that 9-step development cycle. It really starts with the analysis phase.
Right. Steps 1, 2, and 3 are all analysis. Step 1 is just define the problem. Write a clear statement of what you're trying to achieve.
Write a program to find the average temperature, something like that.
Yep. Then step 2 is analyze the problem. Gather requirements, identify constraints. For that temperature problem, how do you handle missing data? What about outliers? This is where you define the scope.
And step 3 is design the solution. This is the how. This is the algorithm stage.
You look at trade-offs, like efficiency versus cost. And the key principle here is modularity, breaking that big problem down into smaller, reusable pieces.
So that if one part needs an update, you don't break the whole system.
Exactly. Once that design is solid, then you can move to implementation.
So step 4 finally is writing the code, the 20% part.
Right. Using your editor or IDE, you translate that detailed design into C++ source code.
And after you write it, you have to build it. Step 5. This is where compiling comes in.
It's actually 2 steps in one. First, the compiler takes your source files and turns them into what are called object files.
And then the linker takes over.
Right. The linker is like the general contractor. It takes all those compiled pieces, combines them with the standard C++ libraries, all that pre-written code, and builds a single, final, executable program.
Once it's built, we hit the validation phase. Step 6, execute.
The loader puts the program into RAM, the CPU starts crunching the numbers.
Then step 7, test. This is where, counterintuitively, you try to break your own program.
You have to. You test it under every condition you can think of. You can do it manually or write automated tests that check the output for you.
And if a test fails, that's step 8, debug.
You find the bug, you fix the code, and then you have to go all the way back to step 5 to rebuild and retest. It's a continuous loop.
And finally, when everything passes, step 9, deploy.
You deliver the finished, working product to the users. That's the whole cycle.
So when you're in that 20% coding part, what does a C++ file actually look like? What are the parts?
Well, every program needs an entry point, the place where it all begins. In C++es, that's a function called main.
And then you have comments, the notes for humans.
Critical. The compiler completely ignores them, but no one can understand complex code 6 months later without good comments explaining the logic.
You also mentioned libraries.
Right. Collections of pre-written code for common tasks, like handling input or output. You include them so you don't have to reinvent the wheel every time.
So you can focus on the actual problem you're trying to solve.
Precisely. Then you have the instructions themselves, the statements that follow the language's grammar, and of course, whitespace.
Which is compiler also ignores.
But which is absolutely essential for human readability. Good indentation makes code so much easier to understand.
And that understanding is key because, as you said, we spend most of our time debugging, fixing things.
A huge amount of time.
Yeah.
And understanding the types of errors you can get is half the battle. There are really 3 main kinds.
Okay, what's the first?
The easiest ones are compile time errors. These are just syntax errors, grammatical mistakes.
Like you forgot a semicolon.
or misspelled a command. The compiler just stops and tells you, nope, can't build this. They're annoying, but the computer points you right to the mistake.
What's the next level of difficulty?
That would be runtime errors or exceptions. The program compiles just fine, it starts to run, and then it crashes.
Like trying to divide by 0?
That's a classic one. Or trying to access a piece of memory you're not allowed to. They're harder because they might only happen with very specific inputs.
But the worst ones, the ones that really cause headaches, are the logical errors.
Oh, the semantic errors. They're the sneakiest.
Yeah.
The program compiles perfectly, it runs perfectly, it never crashes.
It just gives you the wrong answer.
Exactly. You told it to add 2 numbers when you meant to multiply them. The computer did exactly what you told it to do. You just told it the wrong thing.
And you only find those through really, really good testing.
Rigorous testing.
Yeah.
Which brings us right back to why steps 7 and 8, testing and debugging, are such a massive part of the job.
So what does this all mean then? This deep dive really shows that computer science is this disciplined connection between logical analysis
Defining the problem, designing the algorithm.
and the pragmatic, creative process of that 9-step development cycle.
And if you take one thing away, it should be that the true skill isn't in memorizing syntax. It's in those first 3 steps, the analysis and design.
That's where the 80% of the work happens.
That's where the value is created. That's what determines if your final product is going to be brilliant or brittle.
The resources we've shared with you point towards some ways to challenge yourself on this immediately. You should really look into the Caddy's online problem bank.
That's a fantastic resource.
It has hundreds of these computational puzzles that force you to practice that whole cycle, turning a problem into an algorithm and then into code that works. Remember, understanding that 9-step process is so much more valuable than memorizing any specific C++ keyword. Now, what problems are you ready to structure and tackle?